So a qualitative fit may be sufficient to gain insight into the dynamics of an infectious disease. Now, take for instance, now, I was saying the other day that now you are trying to, some of the models you have been developing, like the one Afiz has been taking, you find out that these are models to just understand the transmission dynamics. They are not meant to predict anything. Yes, they are not highly complex models. They are simple models that you can use to understand that disease. You want to gain insights into that disease. So, and that's where we are starting from. Now, if you want to build, I say that, but a good quantitative fit is generally necessary if the model is used to advise on control policies. On the other day, I was discussing the issue of there are two analyses you can carry out, the qualitative and then what? The quantitative. Now, for the qualitative, the people who are in mathematics are interested. Also, some of us who are doing, who are in public health, you could also want to be interested in the sense that, especially if a disease has just started, or like no model for like FGS now, there is no model that have been developed for FGS to understand how FGS is behaving. So for us, we needed to gain insight into how is FGS, how is it behaving? What is the insight around FGS in Nigeria? So in that situation, you are trying to build a model to gain insight into the dynamic of that disease. So, and then in doing that, that does not mean that you don't put essential features. Essential features that makes the transmission. Now, you cannot be discussing such model and you don't talk about their transmission routes. Various transmission routes that are available for you to get the disease. You have to discuss them, and so that the model you are presenting is like bringing forth a framework. A framework. So people are seeing it and then they are saying, okay, that means this is the understanding about this disease. And then we can know now, what's the next thing? People began to think, what's the next thing? What are we going to do? So this is the way the disease is. So it means that, you see now, we're proposing in the model that if somebody is not treated between that age, then there is possibility of she advancing into something that is more problematic. Are you getting what I'm saying now? So the information to the public now is that now what do we do? Now in those identify, because there are hotspots of FGS in Nigeria, hotspots. Now, so people in the public health now, the next thing to do is that, okay, in those hotspots, what are we going to do? There are two things to do. The first one is maybe we need to do mass testing. Now, it may be very expensive, but at the end of the day, it's not economical, but it saves lives. Are you getting me now? It saves lives, because if you test people, it means that you want to give them treatment. So those that are tested and are positive, you are going to do what we call targeted treatment. Because from the public health perspective, targeted treatment is far better than random treatment. Because when you say random treatment, you just at random you are treating people. There's no specification. Now you have not tested. Are you getting what I'm saying now? You just want to, let's assume that there are 1,000 people in a place, and that's why for me in Nigeria, the way we deploy treatment or vaccination, that's why we have not been seeing results, because people go there and they do it without getting the data, and it has really not solved the problem. So the thing is, if you go for targeted, in the sense that you have diagnosed the people, you know the people that are positive, and then those are the ones you have treated, then you will have solved the problem. So what we are saying here is you can go for qualitative fit, which may be sufficient to gain insight So some of us who have been doing mathematical modeling from the mathematics department, what we have been doing is basically to gain insight. And we have been repeating the same process just to gain insight into the dynamics of an infectious disease. Now, but if your model is going to advise on control policies, then it needs to go to good quantitative fit. Then accuracy generally improves with increasing model complexity and the inclusion of more heterogeneities and relevant biological detail. Underline that. Generally improves, it gets better with increasing. Understand the word increasing. That means you can start simple, but you keep doing what? You keep adding up. You keep adding up. You keep adding up. You start simple, you look at the way shape is giving you, and then you add up more stuff, and then it's changing. Let me tell you, if you have a model, and then you have in your model, you have just like the SIR you have beta SI minus beta SI. You know the one that Afis gave us yesterday was some of them he didn't put. It started very simple by not putting. It started with a closed population, and then the one that does not have births and deaths. You understand? Like an adiabatic system. Nothing goes in, nothing comes out. For those of you in physics, now then life is not always like that, because that's for epidemic. As time goes on, the population is growing, right? So as the population grows, what do? You have to include the birth and the death. That's natural death. Now, as you include those things, there's a way it affects the equilibrium. How do you know? Now, what you do now, some of the assignments I'm going to give you is that you are going to find the equilibrium and the plot of S of I. You write it. You find it, you do it. That's part of the assignment. You use your R to do it. Now, you are going to find the equilibrium of an epidemic model, SIR. You find the equilibrium. You also give me the time evolution of S, of I, of R. You understand what I mean? The time series of S. Like you have like this S, I, something like this. Maybe this is S, this is I, this is R. You give me that. Number two, you will also give us as an assignment now an SIR with demography, like the births, the deaths, right? And then it has a mu. It has the death and the death and the birth and the death. And then when you now put in the disease-induced death, that's another problem. Now you are now going to have the one. That's the third one. I want you to gain an understanding there. Now you have three models that you are going to put for me. Let me put it here so that you can see. So the first one is this one, which is the simplest one. Okay, let me just so you have oh yeah, thank you. So you have this one that has everything. So this one now has delta. That delta is disease-induced death. Now, you will see something there by the time you do it. Now, that's death, that disease-induced death that has been introduced will cause a change in the equilibrium property and the stability property of that disease. Are you getting me now? So you will discover that now, having had to add this death, you are going to find the equilibrium solution of each of these, and then you do the plots. So we want to see what will happen afterwards. So let me quickly go. So that's the assignment. Next. That'll be tomorrow now. Yes. So clearly tomorrow, so somebody will come out and show us the results from each of the groups. Now, all the two, you find the equilibrium. You find the equilibrium for the two. And then you do the plotting. Data I. That data is the case fatality rates, or which is the, the disease-induced death. That is death due to that disease. Okay, clearly the visibility of model complexity is compromised by computational power. Now, we're saying that now, if a model is complex, then it requires very high computational power. So, and then the challenge is that your computer may not be able to handle this kind of stuff. You may need a stronger supercomputer. So, mechanistic understanding of disease, natural history, the availability of necessary parameters. Now, consequently, the accuracy of any model is always limited. It's limited. So, like I said, no 100%, not 100% perfect, but at least we can gain some level of interval on our prediction. Now, transparency comes from being able to understand, either analytically or more often numerically, how the various model components influence the dynamics and interact. Take for instance now, how does delta, I want to know, how does delta affect the dynamics of infected population? So I can now say if delta is equal to maybe 0.5, 0.6 or 1 or like that, and then I'm varying it, that means the disease-induced death, how does it affect the population? Are you getting me now? So if I'm varying it, I'm able to see. So from that, you are checking the feasibility of transparency in terms of looking at the aspect of transparency of the model. Now, this is usually achieved by successively adding or removing components and building upon general intuition from simpler models. Now, do you know why we need to build a simple model? Now, the simple model gives us a general intuition about what is going on. That's generally. So it gives you an understanding of the basic thing about the disease. Like, it's like a descriptive analysis. Now, as the number of model components increases, it becomes more difficult to assess the role of each component and its interaction with the whole. Now, transparency is therefore often in direct opposition to accuracy. So, flexibility measures each the ease with which the model can be adapted to a new situation. Now, your model should be flexible. That's what we are saying. Your model should be transparent. Your model should be accurate. But all of these has their own role. Now, flexibility measures the ease with which the model can be adapted to a new situation. This is vital if the model is to evaluate control policies or predict future disease levels in an ever-changing environment. So your model needs to be flexible so that you can always decide to raise new questions. Take, for instance, you have used your model to understand the transmission dynamics. You also want to see that now which of the control measure you are using, if I'm using even if it is one control intervention, Now, what is going to be the effect on the long term you want to see or build some scenario analysis? Now, most mechanistic models are based on well understood disease transmission principle and are highly, therefore, flexible. They are flexible. Whereas black box time series tools like neural nets that may be able to accurately reproduce a given time series of reported cases are less amenable to modification. Like most of the machine learning models, they are black box. They are black box models, so you can't customize them. You cannot change anything. You know, you are just running what somebody has produced. You are running it. You are seeing a curve. You are seeing a shape. Take for instance the agent-based model also, like the E-mode I told you, the open malaria. You are not the one that built it. So the only thing you can do is you put in your data, it gives you the result. You don't understand the underlying mechanism around that model. So these ones, they are less amenable to modification. You can't modify. So models have two distinct roles, prediction and understanding. Two distinct roles, which are related to the model properties of accuracy and transparency, and therefore can often be in conflict. Now, if you want to use your model for prediction, you need to go for accuracy. It must be accurate. The property of accuracy. Now, if your model is going to be to just understand the dynamics, you talk about transparency. Now, we usually require a high degree of accuracy from any predictive model, whereas transparency is a more important quality of models used to improve our understanding of the disease. So prediction is the most obvious use of models. Prediction. Because that helps you to plan. You can plan for the next outbreak. Then it requires that the model is as accurate as possible and therefore includes all the known complexity. Underline the word known. Now, because take for instance when COVID started, people were developing SIR model because they don't know the biology. Now, as you understand the biology, we factor other details about the disease, and then the model is becoming more complex. And then population level heterogeneities. Talking about, seasonality. Talking about other demographic heterogeneities. Now, predictive models can have great power in specific situations, guiding difficult policy decisions, where a trade-off between two or more alternative control strategies exists. When you have strategies, like I told you the other time, 10% LLRN, 20%, even if it is one control. Yeah, 40 seconds. Okay. Okay, thank you. I'm going to stop here. So we'll continue from here.